In this video, we'll focus on a recap of the algebraic methods of solving 2x2 systems and talk about some tips and things that you might want to think about when you're deciding whether or not to use substitution or elimination. So just to remind you of what a linear system is, we have a system of two or more equations that are solved simultaneously. If we have two linear equations, we're looking for ordered pairs that satisfy both equations. So we had two algebraic methods of solving systems. The first one was substitution. In this case, we wanted to solve one equation for x or y, whichever is more convenient. Then we're going to substitute the expression for the isolated variable into the other equation. What this does is it makes one equation with one variable. So then we'll solve that resulting equation. We'll get either x or y, and whatever value we have, we're going to use that value in one of the other equations to get the other variable. Then, of course, we write our solutions as ordered pairs or in set builder notation. For the elimination method, we have to decide whether or not to eliminate x or y, which might be determined by the coefficients that you have. If necessary, you'll have to multiply one or sometimes both equations to make the coefficients of that variable opposites. So we'll talk more about how to make those decisions in this video. Once you have opposite coefficients for either x or y, you'll add the equations together. One of the variables should be eliminated, so should cancel out. Solve whatever equation you have for whatever variable is left, and then use that value to solve either of your original equations for the other missing variable. And then, of course, write your solution as an ordered pair. Alright, so when we're talking about using any algebraic method, if you have to decide which method to use, we should maybe talk about some advantages and disadvantages of each. And also think about what would help you to decide whether or not you should use substitution or elimination. Both methods will get you to the right answer. Alright, so let's look at these examples and kind of talk about them along the way, and then we'll think about why we decided to use substitution versus elimination. All right, one thing I really want to point out before we look at these examples is that the method that I choose might differ from the method that you choose. There are a lot of choices that are to be made when you're solving systems. One could be the method, right? It could be substitution or elimination. But then even once you choose a method, there are other choices to be made. If you're using substitution, do you solve for x or for y, and in which equation? If you use elimination, do you eliminate the x, do you eliminate the y? If you see fractions or decimals, do you decide to clear them out or do you decide to work with them? So all of those choices could change the order or the path that you use to get from the system to the solution. But no matter which path you take, you should eventually arrive at the same solution as anybody else with whichever path that they chose. Let's take a look at the first example. So here we have 2x plus y equals -1 and -3x minus 2y equals 7. So one thing that I do first before I decide whether I'm using substitution or elimination is see if I already have opposite coefficients. The coefficients for x are not opposites, the coefficient for y are not opposites. Then I might have to decide, well, do I want to use the substitution? Do I have a coefficient of either 1 or -1? And I do. I do have a coefficient of +1 in that first equation for y. So this would be a good candidate for substitution because it won't take a lot for me to make this y equals. And I won't have any fractions in that equation either. So for the purpose of this video, I'm going to decide to use substitution for this example. So that means that the first equation needs to be rewritten. So maybe off to the side, I'll think about this equation, 2x plus y equals -1, and just rearrange it, and then I'm going to rewrite my entire system here. So I might be able to mentally rearrange that equation just by subtracting 2x on both sides. I have y equals -2x minus 1. right, so I'm going to rewrite that here for my first equation. Y equals negative 2x minus 1. And again, we're using the substitution method. All right, so my second equation will stay the same. I only need to solve one of my equations for one of the variables. Since I solved the first one for y, I need to take that expression for y and replace it in the second equation. So now my second equation will be negative 3x minus 2 times, in the parentheses, I have negative 2x minus 1. That's what I've substituted. So that's replacing the y equals 7. So that equation now only has x in it. So I'll solve that equation for x, distribute that negative 2, combine like terms that are on the same side, and then subtract 2 in this case to isolate x. So I have an x value of 5. So I'm going to take this x value and I need it to find my y value. Now I could use either of my original equations or other versions of my equation. So equation 1 I've rearranged. I've already solved it for y here. So it'll be a little less work if I use that form because y is already isolated. So y equals negative 2x minus 1, but I have 5 replacing x. So y equals negative 10 minus 1. So I'll have my y value is negative 11. And just for time purposes, I'm just going to write my solutions as an ordered pair. I'm not going to use the formal set builder notation right now. So there's my solution, 5, negative 11. All right, let's take a look at the second example. All right, so again, I want to decide substitution or elimination. And this would be a good candidate for a substitution as well because the coefficient for x is positive 1, but maybe I decide to use the elimination method here because I see that it wouldn't be too much trouble to make the coefficient for x or for y the opposite. If I want to make the coefficient for x the opposite, I can just multiply that bottom equation, the second equation, by positive 2. Just labeling my equations here. So I'm choosing to use the elimination method here, which means I want opposite coefficients for x or y. I chose x, you could also choose y. First equation staying the same, but I like to rewrite both of them. Helps me keep track of everything. Second equation, multiply everything by positive 2. And now once I have opposite coefficients, I could add my equations together. Now you might notice here that both the x's and the y's are canceling out. So we have 0 equals 9 minus 6 is 3. So this can happen. We only really saw this so far when we were graphing, but this can happen when we're working algebraically as well. Both of the variables disappeared. We have a statement. We have to decide if that statement is true or false. This is a false statement. So if it's a false statement, that means we have no solutions. If we have no solutions, our solution set is empty. So you can write the symbol for empty set or write empty set or put the other symbol for empty set, whatever makes sense. So that can happen just like we saw graphically when the two lines are parallel, but algebraically both variables will eliminate at some point and you'll have a false statement. All right, let's look at the next two examples. Number 3, we see we have quite a large constant, and in the second equation we have some decimals. So let's think about what strategy we can use for that one. All right, there's nothing I could do about that large number in the first equation, but maybe I decide to clear out the decimals in the second equation before I think about substitution or elimination. So I'm going to take that second equation and I'm going to multiply it by 100 to move my decimal points all 2 places. So let me rewrite both equations now. The first one stays the same. X plus y equals 10,000. Second one is now 5x plus 7y equals 65000, so 65,000. All right, so now I have to decide substitution or elimination. Both are good candidates because we could easily take that first equation and solve for x or y. I'm going to use elimination here because if I make the coefficient for x or y opposite, I'm going to have negatives, and that's going to subtract. We'll make that constant a little bit smaller. So do I want to eliminate x or y? Maybe I want to eliminate the x value. So let me multiply the first equation by -5. All right, so I went ahead and jumped ahead and did that. So my x's will cancel out. I now have 2y equals 15,000, dividing both sides by 2. And I have y equals 7,500. Now I can use that y value in one of my original equations. I will use the first one. X plus 7,500 equals 10,000, and subtract 7,500 from both sides. So that gives me 2,500. So my x coordinate 2,500, the y 7,500. So again, I definitely wouldn't want to have to graph that one. All right, in the last example here, I have fractions. So I want to go ahead and clear out both of those fractions and both of those equations first before I do anything. So I'm going to go ahead and do that first. All right, so I jumped ahead and did that. You can pause it and take a look if you need the details. But now I see that I have opposite coefficients for x and for y. So both my variables are going to disappear again. So I'm using the elimination method. But this time, the constant also disappears. So I have 0 equals 0. This is a true statement. So this means that both of these lines actually are the same. If we were to graph each of these, they would be at the exact same location. So we have infinite solutions. So when you have infinite solutions, we have to describe what they are. It's not all real numbers because we have ordered pairs. So we have to talk about what ordered pairs do we have. It's not any ordered pair. It's only the ordered pairs that sit on these lines. So I'm going to take one of my equations and just rewrite them so that it's y equals. So I'll take that first one. So let me go ahead and put that in y equals mx plus b. Okay, so I did go ahead and do that quickly. So now I just rewrote the first equation, that y equals mx plus b. And that's because I want to describe my ordered pairs, the set of all x, y, such that x itself can be any real number, but depending on what x is, y is defined as 1/6 of x minus 3. And if I had taken the second equation and rearranged it so that it was y equals, I would have the same exact equation that you see here. So this describes all of the points that live on that line, and the first line is exactly the same as the second line. All right, so just to recap, substitution versus elimination, I would say that go for substitution if one of your variables is already isolated, or if you have a coefficient of 1 or -1 for x or for y. Otherwise, I think elimination kind of works out nicely. The advantages of elimination are you can clear out fractions or decimals by multiplying both sides. And if you have any large numbers, it's kind of nice to use the elimination method as well. But the choice is always yours, and there are lots of different choices that you can make along the way. So no two paths might be exactly the same, but as long as you get to your solution, the path that you chose is appropriate for you.